last class. In today's lecture, we explored a very interesting representation theorem, namely the Riesz representation theorem. Simply says that all continuous functionals in a Hilbert space, all continuous functionals in or each continuous functional on a Hilbert space can be identified with a vector in the space itself and represented through an inner product. Now this is the theorem that we are going to do. So let us make the statement of the theorem and then explore it. And rather than making the statement, I would like to put the parameters there. So H is a Hilbert space. Over C. Let L be a linear function on H. That is, L is a map from H to C, which is linear. Namely, L of alpha x plus beta y equal to alpha lx plus beta. That is the linearity. So it's a linear function. Assume L is continuous. Which means that if xn converges to x, Lxn converges to Lx. So, cell crucial definition. Because this is in C. Okay, so this is a sequence of numbers converging to S. Okay, the definition that is there, valid with the norm defined in C, work C. Okay, so we assume L is continuous. Then shall state the theorem later. Then we prove that there exists a unique y belonging to H such that L x equal to the inner product, which is expressed in terms of the inner product Now this is the representation theorem. See, there exists a unique y belonging to H. So that means that, see, L is a continuous linear functional. Therefore, in the functional analysis language, it is H prime. L belongs to H prime. H prime is the dual of H. It's a dual space of H. What we assert is that the dual space can be identified with the space H itself, or vectors in H manifest as what is called the linear function. Now the reason is this. I mean, this is the so consider a y belonging to. I'm not going to the theorem yet. Let L tilde or Ly be defined by now clearly see Ly is a functional on H. Moreover, from the properties of the inner product, Ly is linear. That's easy to prove. See, Ly of equal to, by definition, it is y, which from the properties of this is equal to alpha or this is equal to alpha L therefore Ly is linear. So you see that once you have the inner product, through inner product or every element in the Hilbert space defines a linear function on H. And through so we have found that there is a class of linear functionals determined by vectors in H itself. So the question that you ask now is every continuous is every continuous linear functional represented by two star. So this is the question that you are asking. Now why I have put continuous here? The reason is this. Obviously, now you see that the linear functional the reason is this. Now remark continuous linear function. That is quite easy to see because this is so. Which converges to x, y zero. That's easy to see. So you can write this as, you can take the difference, it's going to be xn minus x, inner product with y, and you see that this can be estimated is equal to this, and this is less than or equal to by Schwarz inequality which goes to 0. Therefore, these Ly's are all continuous. Therefore, a priori, we should be looking for the validity of this result only for continuous linear functions. Okay. If the linear function is not continuous, then it cannot be represented having this representation because any such representation is continuous. Okay. So, to be true only for continuous functions. This is an important property that we attribute to the linear functional, and only for such linear functionals you can expect the representation theorem to. Okay. So the question that you ask is, does this account for all continuous linear functions? That is our problem. Okay, is every continuous linear functional represented by a vector in H through the representation star? This is the question that you are solving. We shall show that the answer to this is yes. Therefore, what is our job? We are given a continuous linear functional on H. Now we have to identify a vector which is uniquely determined such that for that linear functional L, say L, you have this property that Lx equal to xy. Okay. This is the representation theorem that we are after. So this is valid only for continuous linear functions, and you see that when you work on finite dimensional inner product spaces, all linear functions are continuous. So you don't have to specifically mention that it's a continuous linear function. But then the moment you go to infinite dimensional vector spaces, the property of continuity is something that you have to ask for, because there exists linear functions which are not necessarily continuous. Okay, right. So let us explore this result. Now it's nice to explore this result. It's very interesting to work on our standard model and see what exactly is going on, because we have to somehow zero in on the vector that represents a given linear. Okay. Yes, forgotten. So it is 23rd today. So our problem is this. We are given L belongs to H prime. H prime is the dual of okay. So let us take example. We'll look at the example. Let us take H to be equal to R3 to get some more visibility. Okay. Now, see that let E1, E2, E3 be the standard basis R3. So that is E1 equal to E2 equal to it's a orthogonal basis also. It's an orthonormal basis also. We have norm EI and EI delta Ij. Okay, that means this is an orthonormal basis. basis for R. Now let L denote a map from R3 to R. R is the field associated with R3, which is linear. Now let X belong to R3, then where X is uniquely determines X is equal to X3. Then Lx equal to L of P3. This is equal to plus P3. Because of the linearity, this is true. This is true for every X. One, two, three. Then you see that so let us now look at the geometry. Of the problem. So we take, so this is one axis, this is two axis, this is three axis. Okay. Now Lx equal to 0. And this is a plane passing through origin, whose normal is given by A1, A2, A3. So let us designate this by vector A belong. So you see that, let us draw the picture. It's a plane passing through the origin. Zero. Now just draw the normal to this. Normal is given the direction. This has the property that is right. So this is a line in the plane. So this is orthogonal. So the normal this is a vector in the plane L1 x1 x2. Then this is orthogonal. So you see that this relation can be rewritten as is essentially equal to A dot inner product. Or you can write it even this way. And finally, want this in this form x. It is immaterial in this case because we are using R as the therefore the plane is so we observe that every linear functional in R3 can be identified a plane passing through the origin whose normal is along the vector LE1, LE2, LE3. So note that LE1, LE2, so that is the vector. Okay. So Lx equal to constant is what? Lx equal to constant is a plane parallel to this plane. So this is a unique plane that is identified. Okay. So Lx equal to constant. So you see, once L is given, L identifies given LE1 is fixed. Then equal to 0 is a plane, is the plane okay, let us somewhere for we assume L is not okay. I will explain that out. Is the plane passing through origin with normal P3. Now let us look at what happens. Suppose L is equal to 0. What happens? Let us explore that. Then or the plane essentially becomes the whole space. Okay, it's the degenerate scenario that you have. Okay, so this is the whole space that you have. So let us, that is not interesting because it doesn't give you anything, but this is something which can be treated with just one line when we do the theorem. Okay. So right from the beginning, we keep the assumption for this exploration that L is not equal to 0. So L is not equal to 0. Okay. So you see that the set of all x equal to 0 is a two-dimensional subspace of So if you are working in R2, this is going to be a line which is going to be a one-dimensional subspace of R2. Okay, so it's a two-dimensional subspace of R2. Okay. Which is uniquely identified with the two things, that it passes through the origin as well as its normal is given by A1, A2, A3. Okay. Therefore, there is a unique vector unique direction along A1, A2, A3 which is identified equal to 0. This is the normal, that is A1 This is given by the relation that dot zero. X equal to 0 is essentially this. Okay. So this is a unique direction passing through the origin. So unique line along the vector passing through the origin which is orthogonal to every vector in equal to 0. Okay, so the situation is this. This is 0, 0, 0. This is the direction A1, A2, A3. This is orthogonal thing. we can draw the coordinate system like this. One, two. This is the coordinate system. So you have what you call a line passing through them. Okay, right? Therefore, if span of A1, A2, A3. Okay, that is one dimensional. This is one dimension. So we observe that every linear functional, non-trivial linear functional can be identified with a plane or a two-dimensional subspace of R3. Unique two-dimensional plane passing through the origin since it is two-dimensional. This is not equal to 0 because we are assuming every non-trivial. If you want, you can choose the unit vector in this direction, which is given by, this is, suppose this is A, that is A divided by norm A will give you the unit vector thus there is a correspondence between L is identified with what? The unit vector A. Okay? In the sense that Lx equal to inner product of R3. Okay, and now if you set no, sorry. Okay. Everybody hates me now. Okay, so represent L in the sense that now this is the representation. So we have identified what this vector is. Now A is essentially equal to L1, L2, L. You can generalize this. Okay, so this is our motivation. So if you are working in R2, then the plane passing through the origin will be replaced by a line passing through the origin. Now if you are working in Rn with the usual inner product, then the hyperplane, now this L will be identified with a hyperplane whose dimension is equal to n minus 1 passing through the origin. So there is a unique vector which is orthogonal to that, and that unique vector can be identified with L. Now this is the strategy. Okay. So now we are in a position to state the main theorem. So let me write down the theorem and then prove it. And the proof is now absolutely simple because you know what vector you can identify. See, what you do is you take the plane Lx equal to 0. This is emperor. Okay, so the vector that is going to be identified with well is going to be a vector in emperor. Which vector we shall see. So let me make a statement of it. This is the representation theorem. Unique vector y belonging to H such that so this is the representation where X is a unique vector. So the identification is L is identified with this is the result that we have. Okay. L is identified with Y belonging to H. So H prime is the space of all continuous linear functionals on H. So that's the dual space. Okay, let's move this now. Now you know what to expect. Which vector is to expect, or where do you search for this vector? So the problem is now, see, given a vector in H, you can immediately write down a continuous linear function through this formula. That's straightforward. But given L, how do you pick this vector? So the question is, this is the question that you have. And we have already done some exploration, and we feel that this is going to be along the orthogonal complement of Lx equal to 0. Okay, that's what we have seen. It's a one-dimensional vector space that you get, and that one-dimensional vector space in R3, it's a one-dimensional vector space that you get, and a spanning vector of that is going to get identified with L. Get the point? So let us prove this. Now we have already explored it in this case. First case, the case L is identically equal to 0. That is, X belonging to H. Then take Q so that you see simulation. Well, is identically 0. Now, if so, hence assume L is not equal to now define. We just repeat what we did in the case of R3. Okay. Define M to be zero. Then M is a subspace of H by the linearity of that's easy to see. That's follows immediately. So since L is continuous, we have proved it's a closed subspace of H. That's easy to prove. What you have to prove is that you take a sequence in M, xn belonging to M, and if xn converges to x in H, because if xn is a convergent sequence, it certainly converges to some vector in H. Okay, so you prove that L of that vector is equal to 0. That's easy because L of xn is equal to L of x. Sorry, limit of L of xn equal to L of x because L is continuous. Xn converges to x, like Lxn converges to xn converges to x. Okay, so if Lxn is 0 for every n, then Lx is 0, thereby x is 0. So that completes the proof. Since Lx is not equal to 0 for some x, otherwise L is going to be identically 0. It follows that proper subspace of H. Okay, so M is a proper subspace of H. Therefore, M pair does not contain non-zero vectors. Now, what is our strategy? So, we have arrived at M pair. We shall not bother at the moment what is the dimension of M pair and so on. But at the end of the proof, it will be clear that it is one dimensional. Okay? Or M has co-dimension. Right? So, let us work that out. Okay. Therefore, this is Q x where this is what we have proved last time. And Qx is not equal to 0. This is not equal to 0. Hence, some z belonging to emperor so this is a choice set with the norm of z equal to, that means the unit vector in emperor, some unit vector in. Now we u be a vector defined by Lx so it's a linear combination of z and where the scalars are Lx and minus Lz. So we define such a vector. So it's immediately seen that let us calculate LU. What does this mean? This implies U belongs to. This is the important. Now that implies equal to 0. That means uz equal to the inner product of z equal to 0. Okay. See? Yeah. That's the reason for that. And that implies Lx into norm of zz. We are just just expanding this. Put u equal to this expression or this expression and then expand it. This means, see, this is norm z square which is equal to 1. Or I could say this is equal. This implies that's the reason. So what do you do now? Which further implies Lx equal to this scalar. This is a scalar, which I can take inside. This is equal to x. See, Lz is in general complex, so this will be complex conjugate of that times, so that when you pull it out, become now define Lz bar z, which belongs to so that is the representation here. So we have identified a vector in M pair which represents the one L. So for each L, you have identified a subspace associated with that, namely M. Then you have M pair, and from that you can identify a vector in M pair such that Lx is equal to xy for every x belonging here. So mark. Now we prove the uniqueness. Suppose there are two representations like this, then this implies now as zero. And that in turn implies L is identically zero linear functional, then the representing vector is zero. L is not identically 0, then there exists a unique vector with the property that Lx is inner product of x with y1 for every x without x. Now this is the representation. Thank you very much. We complete here. Two minutes to prove this theorem as such, but I spent considerable example just to demonstrate how the students should pick a example and explore the theorem on that, which will give you a much better insight in what is going on, or what is the statement of the theorem. Just write down the theorem, they prove it, and they don't think about the problem. Okay? So the best way is, before you put your hand on a proof, you explore what the particular theorem means on an example where you have some visual advantage or something, or some geometric insight or something which you can make use of, so that you can see what is going on. And especially in the case of problems invariably you work on where you can draw pictures. Okay? Because in R2, all the non-trivial linear subspaces are line, and in R3, I have taken R3 in this case, so that it should not be too trivial. Like R2, it's easier to draw pictures in R. And in R3, what are the subspaces that you have? The proper subspaces are all lines passing through the origin, which is one dimensional, and all planes passing through the origin is two dimensional. So what we have seen is every linear functional is identified with a plane that passes through the origin, okay? Which enables you to identify the subspace that is normal to it, which is emperor, and there you get a uniquely determined vector which corresponds to the given image. Thank you very much.